Oh, how do I get rid of that? Oh, got it. Whether you can click this one or not. Oh, that one. So let's try with this one. Okay, so welcome everyone to CS Colloquium. So we have a distinguished speaker from the University of Michigan. So long story short, I actually planned we did 2 years back, so before COVID started. And then, I have to attend multiple times. And then now actually we make this, to happen this time. And let me briefly introduce his background. So Dr. Kang Shin is the Kevin Nancy O'Connor Professor of Computer Science at the University of Michigan, Ann Arbor. And he's internationally well known for his embedded real-time and cyber computing. So as an educator, very good. So he has provided completing 91 PhDs and authored close to 1,000 technical articles. And most importantly, he's very active. He's very active in the community. And also, nearly half of his PhD graduates are very active in US companies, in Princeton, also UIUC, and for other places. And yeah, I mean, during that process, he received numerous awards, including several best paper awards in computer systems. So including IEEE William Bennett Award, which is given to the best paper in 3 years. So this paper got best paper, and also several institutional awards, including a Stefan Etlub Award in 2003. That is the highest honor bestowed to the Michigan Engineering Faculty. So, and another one is he also received the 2006 Forum Prize in Engineering, the highest honor for Korean engineering, which I also won in the future. So, and then also he has served on the numerous government committees, such as U.S. NSF Scientific Systems Executive Committee, and the Korean Government R&D Strategy Advisory Committee. So now it is your turn, Dr. Kang Shin. Yeah.
Okay, thank you.
Thanks to the speaker, by the way.
I am really happy to be here, although it took 2.5 years or more than expected. Maybe I think the distance between Detroit and Denver is too far. It took 2.5 years to fly. Anyway, today I'm going to talk about this brand new project. We started August 1st this year, officially, on the Office of Naval Research Sponsorship. Although this project is sort of a culmination of all the things that I've been thinking about and talking about. However, I never presented this before, so I guess the talk could be not as polished as it should have been. But I'll try to give you sort of the more intuitions than detailed results. This is the joint work with my former student, Daniel Chen. It doesn't work. That's what happened. I thought it was working.
That's true. See,
Now,
now it works.
okay, so I'm going to begin with the motivation background, why this is an interesting problem. And then what are the challenges that we have to really overcome? And I'll give you some of the approaches that we are taking. And then give you concrete example of this using semi-autonomous vehicles. And also have a preliminary results of this cat car. I'm not quite sure I'll have time to cover all of that. Well, what are the semi-autonomous cyber physical systems? I think this is has been around for a long, long time. Essentially, what we are talking about is the system controlled by both this automated part and also human operator. So man in the middle loop, sort of the system. Examples like autopilot, started back in 1912, and also the autopilot for the ships, that's the 1920s. And the more recent one would be this autonomous vehicle, having level 0 through level 5, according to this national highway transportation safety authority. I'm pretty sure you are familiar with this, although you've been seeing continuous postponement of level 5 autonomous vehicles availability in the market. Like at the Ford, they say they're gonna make this fully autonomous vehicle available starting 2022, this year 22, but it's not available. They put that off to 22, 25. I doubt there will be fully autonomous passenger vehicles available in year 2025. There are so many variations, and you cannot really fully automate all those things. So I'm not going to spend much of time on this because that's not the focus of this talk. And why are we doing this? The autonomy built into the car, essentially, it could be more safe and consumes less fuel and also generate less carbon dioxide. So it's eco-friendly. And also it's gonna give you more comfort. What are the traditional solutions? Well, I don't know why that top part is covered. We can't control that part, right? Okay, that's okay. That's okay. The title is not that important anyway. What are typical solutions? What are the typical solutions of this semi-autonomous system? It's a common practice. Usually, the priority given to either autonomous part or human operator statically. You don't change this dynamically based on situation. For example, if you deal with cars, you have ABS, anti-lock braking system. If a car skis, the priority given to ABS, meaning that no matter what driver does, car is not going to listen. And how that happens? The car sensors, like the vehicle speed sensors and also engine speed sensors. And then it calculates sort of a slip ratio. If you're familiar with, slip ratio. If the slip ratio is greater than a certain number, ABS will be triggered. So these driver's input will be ignored, but it will follow whatever rules embedded into ABS. That's one. On the other hand, if you look at the adaptive cruise control, you set the speed and then car will adjust this braking or acceleration based on this pre-programmed algorithm. However, if human driver applies a brake, this cruise control will be disabled, ignoring this autonomous control input. So in this same car, in certain cases, you provide priority to autonomous part over human part and vice versa. But you don't change this dynamically. You just assign this priority statically to either autonomous or human control part. Also, they assume these inputs provided by autonomous control part or human control part are trusted. What I'm trying to say, this is not really safe because autonomous control input could be wrong, or human control input could be wrong for reasons such as, say, human operator got tired and make mistakes, or even worse, human operator is malicious, try to crash the plane, just like a German wing, the accident you may remember. So the no perfect human in the loop system, one primary example is Boeing 737 MAX MCAS problem. You guys may remember that there were two catastrophic accidents killing more than 200 passengers each time. And how this system was designed, essentially they tried to avoid these airplanes stalling because the pitch angle is higher than 10 degrees, then airplane will stall. And therefore, if a pitch angle is higher than 10 degrees, even if a pilot is trying to stick up, it's going to be ignored. And the problem is that what happens if sensor is faulty, although pitch angle is less than 10 degrees, but this the pitch angle sensor gives you higher than 10 degrees. And the pilot is trying to stick up because the airplane is nose diving toward the ground. But sensor reading says, no, it is higher than 10 degrees. This MK is supposed to, prevent this stalling. So pilot control signal will be ignored. And then the pilot can disable this by disable this MCAS system and then stick up. But this MCAS sensor will say pitch angle is higher than 10 degrees. Automatically, it's going to come back and then override the pilot's sort of command. So essentially, there was a sort of race or contention between pilot's input and the MCAS input. And then eventually, pilot tries this, disable, try this, disable, try this, eventually run out of gas, no energy, and eventually airplane crashes. So that's the way it happened according to the analysis. And therefore, you may know that the Boeing 737 MAX was grounded for more than a year, costing billions of dollars about the loss, all kinds of things. And then eventually, Boeing came up with a solution. First of all, they provided the redundant sensors, and therefore sensor failure probability will be lower. And if there is a contention between pilot and the MCAS system, the new system will enable pilot to supersede MCAS input. And therefore, pilot can lift up the nose of an airplane, and therefore it's not going to crash. So In that case, essentially you are giving the priority back to pilot than MCAS. Previously, MCAS was given priority more or less. But remember, human can make mistakes because of the tiredness or because of a malicious intent. And another one you can think of, but the Toyota's unintended acceleration. Apply the brake, but car accelerated. And there's so many accidents, so many people got killed, and there was significance of the investigation, all this. I think a conclusion was inconclusive in the sense it could be human error, could it be software glitch, or could it be hardware problems. Although eventually I think they settled out of court. Toyota paying $3.4 billion or something. And the malicious intent, like the German wing flight 9525, this assistant pilot just intentionally crashed the airplane while the main pilot was in the bathroom or something. And there are a lot of solutions. For example, back in 2014, these hackers took over these Jeep Cherokee, and eventually these Cherokee crashed into the ditch and caused, I think, the 1.4 million recalls and costing billions of dollars. And the question is, how do we ensure the control decision is safe or safer to execute, even if there is a possibility that component failures, component compromise, or human errors, or humans' malicious intent? That's the question I want to address. So our solution approach is a CAD/CAR. Essentially, we want to detect and resolve whatever control decision anomalies. Essentially, what it does, it will take a control inputs from both sensors and recommend what are the final actions to take. Essentially, we are trying to add one more layer between autonomous input and the operator's input, and before delivering this control input to the actuator, we want to go through this filter, choosing whichever safer between the two. Existing system does not have this filter in between. Essentially, what we do is we want to see whether there is any anomaly or not. You have to check this. I'm going to explain to you how to do that. And then if anomaly is detected, before you determine this is anomalous, we should ignore. But I want to reason about whether this is really anomaly or in this operation context caused this anomaly. For example, if you apply, say, brake maximally, climbing up hills in San Francisco, the vehicle speed is not going to be the same as driving flat surface. What I'm trying to say is a high upslope is the context of operation, and therefore I want to reduce sort of faulty or false alarms. Otherwise, you can have a lot of false alarms. There are a lot of contexts. And then once I have that, I want to estimate risks involved with either decision. And I want to choose sort of a safe decision if all this context-based anomaly says this is safe. If there is no safe decision, then I want to buy more time, whichever, so less unsafe. That's what I want to do. All right, so the challenge is to achieve this. First of all, when you receive this data, how do you know whether it's a correct or accurate? Essentially, we are assuming that no data in the system can be trusted completely, including human inputs, including the sensors of the ecosystem. Ecosystem is equipped with a lot of sensors, lidars, radars, or human can observe all this, all the sensors this entity may acquire. Also, the other inputs coming from, say, infrastructure or other entities like other vehicles. It's gonna get all these umpteen number of sensors, and I am going to sort of test this. I'm not going to blindly trust any of this data. So any data can be wrong. How to determine whether it's a trustworthy or not? Essentially, what we do is we cross-validate this data based on some correlation within certain set of data we call the detection or verification set. I'm going to give you a little more intuition behind that. Second challenge is, if sort of this anomaly we detected based on this verification set, how this anomaly is detected, what is this operation context of the entity which generated the data, either sensor or other entity. Essentially, I want to sort of determine the operation context that generated the anomalous data, mainly because there could be multiple different situations producing same observed data, although they are very different. How do you do that? Essentially, I want to sort of construct this local view of that entity generated this anomalous data using whatever normal data we can trust, although we don't assume, but we verify. So we call that the reconstruction or construction of the local views. So the challenge is when you have this anomaly and also the operation context, that combination, what are the risks involved in this particular input? I want to assess this risk, and then this will be led to recommendation of a final decision that will be delivered to the actuator. And where does this CADCA exist? CADCA exists on individual entity, say a semi-autonomous vehicle or airplane. All these elements will have either CADCA or not, but I'm focusing on this ego entity, say ego vehicle. My car has this CADCA, getting all these inputs from operator, its own sensors, autonomous part, and the human part, whatever. So let's look at this system. Here, manual control, autonomous control part will go through this CADCA filter, and then control decision actuators, I already mentioned this. And what is the threat model? Remember, when you deal with the security or fault tolerance, always you have to begin with the threat model, which one you want to detect and defend against, or which one you detect and tolerate. So these attack models could be like this, operator can be malicious or error prone, or autonomous controller can be sort of erroneous, maybe algorithm is wrong, or executing platform is wrong, or implementation of those algorithms wrong, all that. And also there could be the malicious non-ego entities, other cars, or compromised infrastructure. Could be anything. Or there could be spoofing attacks, spoofing sensor values, falsifying sensor values. Or even there are compromised components. However, I'm assuming though, the implementation of CAD itself is trusted. Okay, I'm implementing this algorithm in a trustable way. Well, this threat model, I want to a little bit, give you a little bit more details. Actually, they're depending on these different attack scenarios. This CAD considers 3 different sort of the threat levels. The first one, the attack level, is essentially the number of data types under attack, whether it is on the single data types like a position or acceleration, velocity. So if all data that available are erroneous, you can't do anything. I said any data can be anomalous, but if all data is wrong, nothing else you can do, right? So depending on the number of data types under attack, the attack level would be more difficult to deal with or easier to deal with. Another one is I want to calculate this normal data sort of correlation. This can be done based on law of physics. And also the number of entities under attack, ego car, non-ego cars, or operators. There are different number of entities could be under attack. Also, I want to consider whether ego entity itself is under attack. Okay, the simplest thing here is very naive threat model that the attackers can only blindly spoof or manipulate the data without matching normal data correlation. If an attacker is intelligent to know this data correlation, it will generate data that matches this data correlation. Therefore, you can detect anomaly. But the naive case, it does not have knowledge of this normal data correlation and also dealing with only single data. The second threat level is that medium level threat. Attackers know the control behavior of the ecosystem and also can launch attack from a single entity. It knows a sort of normal data correlation compared to this naive, the first, this level 1 threat. And then finally, there is a sophisticated threat where attacks can be launched from multiple entities. There, by the way, ego entity can be anomalous or ego can be normal because multiple entities. The single entity case is just one. And we call these threat level or scenarios S1, S2, S3, S4, and so on. And the more sophisticated threat models you have, the more difficult to defend. So essentially, the Kafka's capability based on this threat model, you can detect anomalies, all three different threat models. The ensuring safety, we can do for level 1 and the level 2 threats, but we cannot ensure safety for these sophisticated threat levels. Okay, let's just delve into the design of this system. I gave you enough motivation, I hope. First of all, I mentioned this detection set or verification set. That's where we check sort of consistency using this cross validation of data using this normal correlation. Suppose that we have data types of interest. I said the data or data types using these two terms interchangeably is more of data types, say position. That's the data type, as opposed to position at time t plus delta, t plus 2 delta. I'm not talking about that, just position data or acceleration or velocity, it's the same thing. So suppose we have the data types of interest, X1, X2, and so on. And I want to divide the data types into groups. By the way, these groups are non-disjoint, that can be overlap. And then you can have the output function or G function there. And what we want to do is we want to estimate and predict and also derive the features for these data types in each group. And then from each group, we are going to determine anomaly or not. And then we are going to compare against each other. And then each group I call the detection set or verification set of data. And this category consists of 3 sequential stages. One is a consistent check. I already mentioned that we are going to use this correlation between data types within each group and determine consistent check, and then produce their detection or not, and then cross-couple between the data groups or the detection sets. And then we have the operation context. And then we sort of determine whether this control decision is safe or unsafe. Okay, so here is an example about this detection set. Suppose you have position, velocity, acceleration, heading, and the yaw rate as sort of the data types or data. If you group, say, position and velocity as a one detection set, remember there's a relationship between position and velocity, as you see here. And the velocity acceleration, you also have this relationship. And based on this law of physics or relationship, I will be able to estimate what position value or what velocity value might be. And the position sensors and velocity sensors will report certain values. And those report or sensitive values are very different from these anticipated values. I will say, oops, this is something wrong. And I do this based on all these detection sets. And then I look at these detection cells reports. And I can perform and operation. If everybody says, oh, this is consistent, then I think the data is consistent. If say one detection says, oh, these are anomalous, I perform and operation. In that case, I'll get sort of the anomaly report. Essentially, you can come up with the integer equation system. You can have this set of equations based on this consistency check. Like this. What we are trying to do is we want to solve this equation system to identify which data type is anomalous. But this is not true yet. I didn't really completely verify yet because this anomaly was because of a certain operation context associated with the corresponding detection set. So what I want to do is I want to look at the local view associated with this detection set and want to sort of consider this operation context. For example, here the entity 0, that's an ego entity. One is a non-ego entity, and reporting the location 020, 00, and the speed 50, 30 is different. You get this as a table form. Is an example local view. And you want to solve these equation system. Turns out to be this equation is not going to produce a unique solution. It's going to introduce many solutions. Essentially, we want to sort of search for this anomalous data, and this problem can be proven to be NP-complete fitting set problem. And therefore, you have to have a heuristic algorithms. Here, I have 5 different heuristic algorithms, like a greedy algorithm. You want to see the particular data type covers all sort of detection set. It's a sort of covering problem you can come up with. That is definitely anomalous. That's a greedy algorithm. And the other one is anomalous individual algorithm, or you trust the ego, but you don't trust the ego, and so on. I'm not going to spend much time on this, by the way. And then individual algorithms will sort of generate these anomalous data according to operation context. I showed you this slide before. Say greedy algorithm will generate without matching normal data correlation, and the ego normal can be corresponding to a trust ego, and so on. Okay, I explained this enough. I'm not going to spend more time on this. So essentially, based on this, you will be able to reconstruct this local view based on normal correlation. And then how do you know whether these decisions are safe or not? You have to have a risk assessment. Essentially, what we are doing is the combination of local views that I constructed and the control inputs. So local view from greedy algorithm, or the trust ego or anomalous ego, this local view generated. And then the control input choices, you have number of control input choices. And then the assess sort of the risk. What do you mean by a risk? Whether this time to unsafe state is, say, 10 seconds or not. Essentially, we calculate for this each local view and the control input pair. So based on this, you can decide which one to take. For example, time to unsafe state. In that case, you want to choose whichever produces the largest value of this, or the time to avoid the unsafe state, or time to avoid the collision. And if this TTU is smaller than TTAU, then I think this is more of a safety concern. Based on this, I think you are going to recommend or choose the final control decision. Obviously, if there is a sort of a safe control decision, you're going to choose that. But if you cannot choose a fully safe decision, what you have to do is you have to choose whichever less unsafe. And also you choose these less unsafe, all that. You do this based on most likely scenario. Essentially, you do more of this reputation thing. In other words, one particular entity or this detection set reported anomaly, multiple times in the past. You maintain these counts, and based on counts, you trust more or less particular results. I have 10 minutes.
Yeah.
Okay. So let's look at example here. We considered 3 vehicles. Here, this the ego vehicle, and this another vehicle. This ego vehicle has its own sensing capabilities to measure speed, heading, or whatever, and also it has this external data available coming from different cars, like a basic safety message protocol. You may have heard of that. Initially built on DSRC. But anyway, you can get this data, or you can get this data from infrastructure, such as the roadside units, or traffic light controllers, whatever. And then there's the non-ego entities will broadcast its own measurements using, as I said, the PSM, basic safety message protocol. And then this ego vehicle gets its own sensor readings and data received from non-ego entities. And as I said, these attacks can be made on these ego vehicles sensors, such as a sensor falsification attack, or this broadcast data can be compromised. Either this non-ego vehicle itself is malicious, or there is a communication attack in delivering this broadcast information to ego vehicle. So, as I said, we have to do this the consistency check. essentially this detection set is based on this the ego and the vehicle one sort of the data, that the E1, E2, E3, E4, E5 is the ego-centric then. This one is from vehicle one. And then this last row indicates a correlation of distance measurement of these two vehicles location. Remember the individual vehicles will report measure and report distance according to PSM protocol. It has that. And then these data in a detection set all have unsuccessful match with each other. And then that will be led to sort of equation system I mentioned. Say if this measurement is anomalous, it's going to generate 1, otherwise 0. And then you solve this equation system with these 6 different heuristic algorithms I mentioned. So receive the data and the consistency check, and then you come up with the solutions and local views. And then you come up with these table having this location and the speed, and there is some sort of the red color is anomaly. We detect that. And then, as I said, we calculate this time to collision or minimum required response time. Actually, this minimum required response time is based on people's reaction time. If they find something anomalous, how long does it take to react? And so according to the reports that we saw, yeah, I don't want to go over this. It takes about 2.6 seconds here. And also the medium driver reaction time for, well, you have to worry about the smooth maneuver. That's very important for autonomous vehicles. Remember, the most autonomous vehicles are not traveling faster than 15 miles an hour, like a Google self-driving car. I think the maximum speed was 15 miles an hour, mainly because the maneuver control is not smooth. And if it makes a sudden stop, passengers will bump their head to windshield or seat, all kinds of problems. So they looked at these the smooth sort of the driver reaction time and built into autonomous vehicle. And the urgent situation is 2.6 seconds, I mentioned to you already. And the minimum required time to avoid the collision, that depends on speed of vehicle, by the way, as you know. And if there is the safe decision, you choose always a safe decision. Say control one says safe in all local views. Definitely I'm going to choose this. If there's no safe control decision, then you're going to choose whichever has the largest time to collision. Therefore, this ego entity will buy more time. And also you have to do this based on the sort of reputation I mentioned already, based on past history. And essentially you do bookkeeping on anomalous count. And I want to do sort of weighted anomalous count. In other words, this anomalous count long time ago will receive a much lower weight than more recent one. And based on this weighted anomalous count, I would like to have more sort of probable or believable local view as opposed to treating all local views equally. And then you have to normalize all of that. So here's a control 1, control 2. This is a local view one. Remember, in this case, neither of these two control produces safe assessment for all local views. Right? Unsafe. Oops. So all being equal, you want to choose whichever produces a longer sort of the time to collision. You can choose local 1. And also remember the here local view 1 is more likely true or trustable based on this weighted anomalous count. So we choose the control decision based on most probable local view, which was local view 1. I have also the evaluation on general sort of these CAD scenario, not just the cars, essentially using metrics of the successfully preventing these unsafe controls and also incorrectly blocking these right control system, because this is also the false alarm type thing. So we evaluated this based on JSIM, which is I think widely used the automotive simulator, because you can't collect this data on real vehicles. Actually, data is not available anyway. So we had a lot of testing cases as shown here. And we simulated this while manipulating, say, vehicle speed. Vehicle speed are manipulated to deviate from true value, say, 18 to 54 kilometers. There's a lot, large variations. Obviously, in that case, you have a more or higher success rate, and also the low incorrectly blocking the decisions. And also we simulated when this deviation of speed, it was 6 to 9 meters. You're going to have a lower success ratio and also the higher incorrect sort of blocking rate. Okay. I think this is the end of my talk. Essentially what we did, I think we are trying to sort of develop more actually safe way of choosing control decision for this semi-autonomous cyber physical system. And the applicable system could be semi-autonomous vehicles, airplanes, or mobile robots, or drones, or even ships. And we proposed a sort of the general system architecture and looked at sort of domain-specific sort of design aspects. And what we are currently working on, I want to dig deeper into, say, MCAS problem. Turns out to be MCAS problem is much simpler than autonomous vehicle, because you're not dealing with so many different entities around this ego entity. Whereas autonomous vehicle case, you can have 2 cars, 3 cars, 5 cars, depending on how many lanes you have, and so many different entities involved. So I said, let's do this a simple case first. So we've been looking at this MCAS problem and digging out all the details of MCAS design and the reports, all that. And I found that it was not as simple as I initially thought. So we are currently writing that up, hopefully submitting to University Security on October 11th. But there's a possibility that we may not be able to meet the deadlines. My generic philosophy is that we're gonna do the best we can to meet deadlines. But if it's not ready, it's not ready. I don't push my students myself. Well, we're gonna meet these deadlines regardless. You know what? If you do that, you may end up with having sort of some dishonesty built into. Perhaps you guys heard of that University of Florida, the ISCA paper, and student killed himself. Okay, so this academic honesty or this data integrity, all that stuff, that is more important than having more papers and prestigious venues. So I guess it's over 60% of chance that we may finish something reasonable. But if not, we're gonna wait until S&P deadline in December. Okay, I think I ran over gas time as well.
Okay, thanks to the speaker.
Yes.
We will take a few questions, and.
Yeah, I have a question. Thank you for your talk. Is there a severity of attack that would prevent Captain from determining which of the local views is most likely?
Local view what?
Is there a severity of attack that would prevent Captain from determining which of the local views is most likely?
Oh, that is that's based on, as I said, the weighted anomalous count. For example, if one particular entity reported this anomalous data very frequently and recently, I like to say that entity's report is likely to be anomalous. And that's just heuristics. I'm not saying it is 100% accurate. And as I said, this is still early stage. We have to look at more case studies to build more confidence in it.
Okay, so I think I misunderstood you earlier. So you're using the counts to determine whether an anomaly is true, but also to determine how much you trust each local.
How much what?
I mean, you're using counts to determine which anomaly is true, but also to determine which local view is trustworthy.
Yeah.
Okay.
That's what we do, yeah.
I want to ask, the weighted anomalous count, it says that it depends on the vehicle being anomalous. So I wanted to ask, in case of a vehicle, is this computed for what it was reported by the model of the vehicle or by that vehicle itself before being repaired?
That's a good question. Actually, we have a very simplistic sort of thing, assuming that I know which entity reported or what. If the reporting entity itself is sort of hiding its own entity or masquerading to be something else, we are not addressing that part. Okay, that's a different question. So if I know it is coming from, say, entity X at time t, t plus delta, t plus 2 delta, whatever. So I have a history of that entity's report. So just like if one person has been unreliable for many times in recent history, whatever that person says, I'm gonna trust the last. That's the idea. It's a very simple-minded sort of the notion that which local view is more trustable. Actually, it's not entity. We are talking about local view says this is anomalous, this is anomalous, all the time it says. So that's what we are doing here. By the way, this the local view is related to entity or entities of the surrounding or local view. So entity and the local view can be viewed as the same thing. Just like when you work with a number of students, some students always late. I'm gonna finish this by tonight. I don't hear anything. I wait for a week. I don't hear anything. So what's the status? Oh, I'm still working on it. So next time now, I'm gonna finish this by this weekend. I don't trust that. And I see some students like that. But my case, if I do that, I feel really guilty. I'm not gonna promise anything anymore. But some students always do that though. But the person is not a bad person. He's a very good person. But that's his personality. So that's the way you build a reputation or bad reputation, I may call. So this is just the simple heuristics. There is no rocket science. I don't think you can find a control theory here.
I have a small question. So how do you compute this time to collision?
Oh, time to collision. That depends on, actually, as I said, you detect an obstacle. And also you estimate how far that obstacle is away from you. And also how fast you're driving. You have to have all this information. And also how long it takes to brake. You know, when you apply brake, the car is not going to stop instantaneously. So you can calculate this using dynamics. And that's a harder problem, in fact. I think a lot of people worked on these autonomous platooning of trucks and vehicles. Remember, you have lead vehicles and followers, right? And if a lead vehicle suddenly brakes, then following vehicle must stop without colliding it, right? And when you take a driver's license test, depending on how fast you drive, you have to maintain safe distance, say 1 car length for every 10 miles an hour, right? That's what you learn, right? That's because it is going to take that much of a time. If you drive 60 miles an hour, even if you apply brake, the car will travel 6 car lengths before it stops. So you have to have all this information to determine time to collision. And also we add how fast the people can react. You detect this obstacle, you apply brake. That's not instantaneous. And there is sort of a study on how long it takes to react. So we add these dynamic equation-based sort of collision and time to collision, add that human reaction time for it. That's what we calculate.
So you don't assume non-determinism of your model.
No, I think we are sort of calculating for the worst case if possible. And how do you know this is the worst case? It's empirical, unfortunately. There's no absolute value. Even human reaction time, that's empirical. Some people may take even, say 5 seconds, not 2.6 seconds, depending on how agile you are. If you're agile, it will be quicker. But if you are as old as I am, it might take 5 seconds. So there is a large variation. But this is just a case study. I'm not saying this is a crowd truth, and this is so written in stone. It's not. It's an idea how we can do it.
Okay, so, thanks to the speaker again. Stay here for another 20 minutes, so if you have more questions, then come and then